This video is about the polygon angle sum theorems, and we're looking at angles inside and outside of polygons. So first, let's talk about what a polygon is. On the left are a couple of examples of things that are polygons, and on the right are things that are not. Now, there's a couple things that I'm hoping that you notice. One is that on the left, they are all closed figures. Okay, they're closed figures, whereas this one is not a closed figure. Okay, also I hope you notice that they have straight sides. Okay, there are straight sides like this one, this right here, does not have straight sides, so it's not a polygon. Okay, the other thing is that it can't overlap itself. Okay, like this one does. So the definition that we have for a polygon is a closed figure made of straight sides where each segment intersects two other segments at their endpoints. But basically that last part means it doesn't cross itself. Okay, now there are different names for polygons, and you should be familiar with these names. You're probably familiar with many of them. Like a triangle has 3 sides, a quadrilateral has 4 sides, a pentagon 5 sides, hexagon 6 sides. A heptagon is not as commonly known. A heptagon has 7 sides, an octagon has 8 sides, a nonagon has 9 sides, a decagon has 10 sides, and a dodecagon has 12 sides. Okay, anything else is that number gone, like an 11 gon, or a 15 gon, or a 37 gon. Okay, you just put the number and then say gon. Okay, so here's some important vocabulary about polygons. Okay, equilateral polygons, lateral meaning side, where all the sides are the same length. Okay, equiangular is where all the angles have the same measure. Okay, now one that you're probably not familiar with is the term regular. Okay, a regular polygon is both equilateral and equiangular. So let's look at some. Okay, this rectangle is not equilateral because they're different lengths. It is equiangular. Okay, because all the angles are 90 degrees. Okay, so it's not regular because it's not equilateral. Okay, this triangle is both equilateral and equiangular, and so it's regular. This hexagon is equiangular, as it says in the angles, but this side looks longer, and so it's not equilateral, and so it would not be regular. Okay, down here, this hexagon is equilateral and equiangular, so it's regular. Okay, this hexagon does not look equiangular because this looks smaller than this. And so it would not be equiangular, and it would not be regular, but it would be equilateral. Okay, finally this octagon, oops, that's 6. This octagon is equiangular and equilateral, so it's regular. Okay, moving along. A diagonal is a segment between 2 vertices that is not a side. Okay, so this is a diagonal, and this is a diagonal, and let's see here. This is a diagonal, this is a diagonal, okay? You connect 2 vertices and it's not a side. That's a diagonal. Now that's important for us because it kind of will use that in finding the measures of the sum of the angles inside of a polygon. Now, a convex polygon is where no diagonal contains any points outside of the polygon. Okay, so these are convex polygons because any diagonal that I draw will always be inside the figure. Okay, concave polygons is where there are diagonals that go outside. For example, this one is outside and this one is outside. Okay, or this one is outside. Okay, now in general, the polygons we talk about in this class are almost exclusively convex polygons, unless we say otherwise. Okay, now that we have all that vocabulary out of the way, let's talk about angles inside and outside of polygons. This is the important stuff in this section. We know that the angles in a triangle add up to 180 degrees. In fact, we've even proven that to be true. So let's look at quadrilaterals, pentagons, and hexagons. Now, as much as possible, we like pulling things back into triangles because we know so much about triangles. Okay, so I'm going to draw some triangles inside of these polygons to help me figure out the sum of these angles. So I want to find the sum of these 4 angles in a quadrilateral. Okay, and I will do that by drawing in some diagonals. Okay, I'll pick one vertex and I'll draw in all the diagonals. In this case, it's only one. Now, a quadrilateral has 4 sides, and by drawing in this one diagonal, I've created 2 triangles. Okay, a pentagon, I'll take one vertex, draw in some diagonals. A pentagon has 5 sides, and there are 1, 2, 3 triangles. A hexagon, again picking one vertex, hexagon has 6 sides. I draw in 1, 2, 3 triangles, and I have diagonals. I have 1, 2, 3, 4 triangles. Now, hopefully you notice something, that there are always 2 fewer triangles than there are sides. Okay, so if I let n be the number of sides, the number of triangles that there are will be n minus 2. Okay, so if I take like 6 sides for a hexagon, 6 minus 2 is 4. So this is the number of triangles. And that leads us into the formula for the sum of the interior angles of a polygon. Okay, make sure you have these in your notes because it's really important. Okay, n minus 2 is the number of triangles, and that's multiplied times 180 degrees, because that is the angle sum in each of those triangles. Okay, so n minus 2 times 180. Here is one quick example. We have 1, 2, 3, 4, 5, 6, 7 sides. This is a heptagon. And so the sum of the interior angles will be 7 minus 2 times 180. Now 7 minus 2 is 5. So 5 times 180 is 900 degrees. So the sum of these interior angles will be 900 degrees. Let's talk about regular polygons. Okay, the measures of each interior angle. We know the sum would again be n minus 2 times 180. But what about each interior angle? Well, let's see here. This pentagon has 5 sides. So I know the sum will be 5 minus 2 times 180, or 3 times 180. Is 540. Okay, but I know something about regular polygons. They are equiangular. So all 5 of these angles are all the exact same measure. So I can divide this by 5 and get the measure of each of those angles to be 108. Okay, so in general, the measure of each interior angle of a regular n-gon will be the n minus 2 times 180 for the sum, and you will divide that times n because each angle is the same. So this is the formula for each interior angle of a regular n-gon. Okay, now let's look at the angles outside of polygons. Okay, so I've kind of extended the sides and drawn in the exterior angles. Okay, and I'm going to extend them a little bit further just so you can see what I'm talking about. Okay, now you may notice something about this angle, and this angle, and this angle, and this angle. And just so you can see it even better, let me kind of draw it even bigger. This angle, and this angle, and this angle, and this angle. Okay, the sum of those angles go all the way around the shape, and so the sum is 360. Okay, the same thing happens with this angle, and this angle, and this angle, and this angle, and this angle. So the sum of the exterior angles will always be 360. Okay, and that's the polygon exterior angle sum theorem. The sum of the measures of the exterior angles of a polygon is 360. That's true for any convex polygon. Okay? Now, so let's find the measure of each exterior angle of a regular n-gon. Here's a pentagon. We know that the sum of the interior angles of a pentagon is 360. And because the insides are all equally angular, so will the outsides. So there are 5 of them. And I'll take 360 divided by 5 and get 72. Okay, or in general, the general formula would be 360 divided by n. Okay, and that wraps up this video about polygons and some angle sum theorems both inside and outside of polygons. We talked about some important formulas. Make sure you have those 4 formulas down in your notes.